two more specialty graphing things to do. So you've got your regular graphing. That's how we started the year with transformations. And you had all your parent graphs and things moved left, right, up, and down. And so we graphed a whole bunch of functions. Then we added sine graphs and did like the DAB-C. Then we added log graphs. So we have a lot of graphs that we graphed directly, and then we had some specialty graphs. The first specialty graph that you looked at was what happens if you put anything inside of a square root. And we kept 0 and 1s the same, and between 0 and 1, the y values were slightly above, and when y values were bigger than 1, they were below. And what we have left as far as specialty graphs go, we are first going to do, what if we take any graph that we already know and put it on the bottom of a fraction and do 1 over it? You've done 1 over x, but that's the only one you've done so far. Well, technically, you did 1 over x squared in grade 11, but sometimes that unit is really fast in grade 11, so we need to review that anyways. And then after reciprocal functions, we're going to look at what happens if we take any graph that you already know and put it inside absolute value graphs. So these are like 3 specialty graphs in addition to all the graphing you've done so far, which is quite a bit. First of all, the reciprocal graph is not the inverse function. So when we're writing in function notation, even though exponents, you know, a negative exponent means move it to the bottom, in function notation, the negative exponent is explicitly an inverse function. That's where you switch to x and y. And 1 over f of x is the reciprocal function. The rule is really simple. But what happens with that rule creates some very weird looking graphs. If it was really simple, this is all I would give you, and we would be done the lesson, and we'd be like able to move on. The simple idea is as follows. If you wanted to graph the reciprocal graph, 1 over f of x, well, f of x represents the y values. All that you're doing is taking any point on your original graph, x comma y, and you're changing the y point to 1 over y. That's the rule. That's the only thing that happens. It's the same thing, right? When you graph this, your point on your original graph, all that happened was you square rooted it. And with the square root graph, we'd be like, oh yeah, the special things, no negatives were allowed. 0 and 1 are the only ones that stayed the same. So with each of these specialty rules, there's some patterns that we notice that help us graph it quicker. So these steps look at those patterns. Okay? We're going to draw the bottom function first. Just like in square root graphs, you're going to draw your bottom graph first. Then, steps 2 and 3, you can think about as asymptote steps. Okay? And usually it says on a separate graph. A lot of times we do it on the same, we usually do it on the same graph. Draw vertical asymptotes wherever you have x-intercepts. Because if the bottom is 0, that's not allowed. So wherever your original graph was equal to 0, aka the x-intercepts, your reciprocal graph won't be allowed. And when you have a non-permissible value, we've learned that in a lot of units, you get that vertical asymptote. Same thing will happen here. So the bold is the big idea, and then the lighter print is an explanation. So it's saying that if you had the point 3 comma 0, it would change to 3 comma 1 over 0, and that's not allowed, so that becomes an asymptote. Step 3 is also about asymptotes, but it's horizontal asymptotes. If your original graph either goes up or down forever to positive or negative infinity, you will also have an asymptote at y equals 0. And this is connected to a lot of stuff that we did in chapter 2. Remember with reciprocal graphs, if the degree was bigger in your denominator, you always had an asymptote at y equals 0. Well, if you have 1 over and you have something bigger on the bottom, chances are you're going to have that asymptote also at y equals 0. So there's a little bit of overlap from chapter 2 with the reciprocal graphs. And then steps 4 and 5, you can just change 4 and 5, make it simpler for yourself. You can combine these together. Just easy to call them nice points. If you know a point, then you can change that point to 1 over the y value. So if you know a point on the original, you can graph a point on your reciprocal graph. And finally, once you have a bunch of points and your asymptotes, you just draw your graph towards the asymptotes, much the same that we did in chapter 2. So this first page is explaining the ideas of what happens when you do a 1 over f of x graph. And the idea is all that's happening is your y values are changing to 1 over 1. But it causes a bunch of asymptotes to happen, so that's kind of unique. But other than that, I think you'll find it fairly straightforward. And you would have done this in grade 11 in your last unit. So part of this will be a review. This is a grade 11 question. And I wrote out all the steps on this piece of paper, but we're just going to, at the same time, draw it out. So I'm going to put a little graph beside me. You can draw along with me. The original graph is drawn right here. And I've labeled some points on it. We could label some more points on it. For example, would you agree if you plugged in 3 for x, 9 minus 3 is 5, so negative 3 would also be 5. You got negative 2, 0, 2, 0, 0, comma, negative 4. You could even plug in here 1, comma, 3, negative 1, comma, negative 3, sorry, 1, comma, negative 3. On x squared minus 4, it would be easy to draw a lot of points. So in drawing 1 over that, using the reciprocal steps, does this parabola have any x-intercepts? Absolutely. Here at minus 2 and here at 2. So on our graph, at 2 and at minus 2, we're going to have asymptotes. In a reciprocal graph, if the arrows go up forever or down forever, you will have an asymptote at y equals 0. Based on chapter 2, we have a bigger degree in the bottom of your graph. But the arrows are important because sometimes on the exam, they'll just give you a random picture of a bunch of lines, and then you have to look at that picture and say, if my graph goes up forever or down forever, on the reciprocal graph, I'm going to have an asymptote of 0. The logic is as follows. If your graph has arrows going up forever, does it make sense that your y values are getting bigger and bigger and bigger? And if you do 1 divided by a number that gets bigger and bigger and bigger, it's going to get closer and closer and closer to 0. So, as far as reciprocal graphs and making the steps even simpler, 1, draw your original graph. 2, do all the asymptotes, horizontal and vertical. 3, find some nice points. I've got a bunch of points labeled on here. What's going to happen to negative 3, comma 5? It's going to change to negative 3, comma 1 over 5. What's going to happen to negative 1, negative 3? It's going to change to negative 1, comma 1 over negative 3. What's going to happen to 0, negative 4? It's going to become 0, comma 1 over negative 4. And I could do this point as well. And I could do 3, comma 5 will be 3 comma 1 over 5. And I have points in every section. We draw it towards the asymptotes. And from chapter 2, do you remember that in chapter 2 when we did polynomial functions, that the only place you could have an x-intercept was if your numerator is equal to 0? In a 1 over f of x graph, your numerator is always 1. It's never equal to 0. So there are going to be no x-intercepts, ever. I don't know if we want to go back to our... that a 1 over f of x graph has no x-intercepts. And this is the idea. Now, if you did this one in grade, for the grade 11 parabola ones, I gave names for each of them. I don't know if your teacher gave names to them. I called this one the sad face. It looks like a frown and 2 droopy eyes on the side. It's kind of sad. So from grade 11, the sad face, sometimes I call it a sad clown. I don't know if it looks more like a clown or not. I'm not sure. You might realize, now that you've been in my class for a whole year, I have a vivid imagination. I'm sorry. Okay, graph number 2. It's another parabola. And again, right beside this, I'll draw. So step 1, draw the original. It has 0 comma 1. It would have 1 comma 2. It would have negative 1 comma 2. You could plug in 2 and get 2 comma 5. And negative 2 comma 5. Lots of points you could draw on your original graph. Then when we go to graph our function, do we have any x-intercepts? No. So there are no vertical asymptotes in this one. Does the graph have arrows that go up forever or down forever? Yes. So the only asymptote we're going to have in this one is a horizontal asymptote at y equals 0. Next, nice points. What's going to happen to negative 2 comma 5? Negative 2 comma 1 over 5. What's going to happen to negative 1 comma 2? Negative 1 comma 1 over 2. What's going to happen to 0 comma 1? 0 comma, now I'm going to write 1 over 1, but can you see that that's going to stay the same? Sometimes the exam is really particular about y values of 1 and negative 1. Because if the y value is 1, 1 over 1 is still 1. If the y value was negative 1, 1 over negative 1 is still negative 1. So those, in our notes, I had a special note about those, calling them invariant points, points that don't change. Sometimes the exam really likes it if you highlight where the y values are 1 and negative 1, because they don't change. Same thing in our square root graphs. But in our square root graphs, it was 0 and 1 for y values that didn't change. In these ones, it's 1 and negative 1. And we could keep going. We have 1 comma 2, so that's going to be at 1 comma 1 over 2, and we have 2 comma 5, which is 2 comma 1 over 5. If I join the parts in the middle, it's going to go towards the asymptote. Did you do this one in grade 11? I have a name for this one too. Did your teacher give this one a name? The speed bump. I called it a little speed bump. Right? Sometimes the parabola is underneath, and then you make the official graph of Winnipeg, the pothole. Right? Because if the parabola is down, you'd have the same thing underneath. It'd be like a little pothole, which is the official graph of Winnipeg. They're fixing them, some of them. Because there was, on my way to work, there was 2 very big potholes. And then they stayed, but then over the next couple of weeks, there would be the big potholes, and then on the side, there started to be a collection of hubcaps. Because people would hit them and their hubcaps fly off, and then people would stack them on the side of the road. But I think I was getting good at missing them, and I actually had a slight bit of disappointment when they fixed one of them. I was like, oh, I knew it was coming, but it's probably a good thing. Okay. So the 1 over parabolas and 1 over lines were part of grade 11 pre-calculus. Grade 12 pre-calculus says we can put anything on the bottom. We could put a log graph with 4 transformations on the bottom. You'd have to graph that first, get that graph, and then do the 1 over graph of what was the result. So it wouldn't be uncommon to say, hey, you have to graph 1 over the square root of x plus 4. First, you would graph the square root of x plus 4, which is just your square root graph, moved 4 to the left. Or I guess you could use chapter 2 and draw x plus 4 and do the square root using that method too. Next, right beside this, I'm going to do the asymptotes. Do I have any x-intercepts? Yes, at -4. So at -4, I draw an asymptote. Does my graph go up forever? Yes, it does. There's an arrowhead. It is going slowly up forever, but it's still going up forever. So we will have an asymptote at y equals 0. Next, do I have some nice points? Yes, -3, 1. That'll become -3, 1 over 1, which of course stays the same. And 0, 2, that will become 0, 1 over 2. And once you have those 2 points, you have enough to go towards the asymptotes. Notice there's nothing in the original graph less than -4. So you're going to have nothing less than -4 on your reciprocal graph I. So one of the things with reciprocal graphs that's a little bit tricky is your final answer doesn't look anything like your original graph did. But the steps are fairly straightforward. And typically this is what the exam likes to do. They like to give you a random graph with lines. It technically is easier because usually step 1 is you have to graph what's on the bottom yourself. On the exam, they like to give you the graph. So life is a little bit easier here because this graph would already be given. And then we have to, right beside it, draw the reciprocal graph. So I'm going to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 3. Do I have any x-intercepts on my original graph? Yes, I have 3 of them. So at -1, at 2, and at 5, those will all be asymptotes. There is no arrowhead on the end here, but there is an arrowhead on the end on the right-hand side, showing that it goes up forever, so we will also have an asymptote at y equals 0. Now we take our nice points. -5, -1 will become -5, 1 over -1. And if you don't want to write the 1 over -1 and write -1 right away, that's fine. Can you see that a straight line will be a straight line in a reciprocal, no matter where it was? If the straight line's at 2, they'd all become a half. A horizontal straight line is what I mean. This horizontal straight line all the way to -2, -1 will stay a horizontal straight line. Then after that, it's going to go towards the asymptote. Does it make sense that it has to go down towards the asymptote? Because if you went up, you would have an x-intercept, and 1 over graphs never have x-intercepts. Here, we're going to have 0, 1. And it too has to go up towards the asymptotes because it can't have x-intercepts. We're going to have for -1, down towards the asymptotes. And we have 6, 1. And here's the final graph. You have to be tempting. Yeah, I mean, you're going to be tempted, like on the left-hand side, to add an arrowhead. The original graph didn't have an arrowhead. Don't add the arrowhead. Make sense? It's so tricky because on all those other ones, you probably lost some E9 errors during the year for not including arrowheads. And then you get an E9 error because you added an arrowhead when you're not supposed to. I guess the main idea is pay attention because they're going to see if you're paying attention on all of those graphs. So those are basic reciprocal graphs. And again, most typically they give you one like example 4 on the exam, but they could ask you to graph 1 over anything. They could give you a polynomial function with bends and bounces of degree 5, and then you have to do the reciprocal graph of it. Could happen. So anything that you've graphed so far is fair game to put on the bottom of that function, including some special ones, which are sine and cosine graphs. And I have a separate set of special notes for you for that. So I'll hand those out right now. So you remember from trigonometry that cosecant theta is 1 over sine theta. Well, now you're going to be asked to graph cosecant theta. And the idea of graphing cosecant theta is we use what we just learned about reciprocals. If we can graph sine, we can graph the reciprocal. So for each of these, I've given you the original graph. But you would have to draw sine on your own. I'm a little bit mad at my graphs because I gave way too many intercepts. You have to draw a lot of asymptotes based on what I gave you. That's okay. Maybe it's therapeutic. We'll think that one. No, it's not therapeutic. I think so. We'll okay. So, here's sine. Wherever you have, so you would graph sine first. And I did it from negative 4 pi to 4 pi. I should have just went negative 2 pi to 2 pi, but it is what it is. Wherever you have an x-intercept, you're going to have a vertical asymptote. So this is where drawing a bunch of dotted lines will be therapy. I'm going to say that. It's relaxing. Okay, I'm relaxed. I could be done, but no, I have more. Technically, we could label them all, but we'll just label one. Are you okay with that? Does the sine graph go up forever, or does the sine graph go down forever? No. We do not have to draw the asymptote at y equals 0. So just these asymptotes. Next, we have to find some nice points. This is a nice point at pi over 2, 1. If I did the reciprocal of that, I would have pi over 2 comma 1 over 1. And you see that that would stay the same. In fact, all of these maximum points are all values where the y value is 1. All of these minimum points are places where the y value is -1, and if I did 1 over -1, they would stay the same as well. Does that make sense? Technically, you have enough information to draw your graph. If you wanted to have, like, from your unit circle, what is sine of pi over 6? Yes, you do have to have this memorized for your exam. You don't get your pi plate on your exam. Do you remember what sine of pi over 6 was? There was 1, I said. If you memorize just 1, you can figure out all of the other ones quickly. It's 1/2. And if you did the reciprocal of 1/2, you would get the flip 2 over 1. Right? Because the reciprocal, you could do 1 over 1/2, but dividing by a fraction is multiplying by the reciprocal. So the idea of the reciprocal graph, you can take fractions and just flip them. You would get 1, 1/2 would change to 2 over 1, and it kind of makes sense that this should go up towards the asymptotes, because if it went down, you would get x-intercepts, and 1 over graphs don't have x-intercepts. Except for cotangent, which we'll get there, it has its own, a few of its own special rules. Again, now we just draw them up towards the asymptotes, and this is the graph of cosecant. Looks like a bunch of little parabolas. Then secant. First you'd have to graph cos. Oh good, it's from -4 pi to 4 pi. So everywhere you have x-intercepts. Draw your vertical asymptote. Maybe having so many x-intercepts is good for you to help you remember that on a reciprocal graph, wherever you have x-intercepts, you have vertical asymptotes. Do we have one at 0? No, because our graph doesn't go up or down forever. In fact, just like cosine and sine are very similar, the graphs of secant and cosecant are very similar. Does it make sense that all of these maximum points at 1 will stay 1? And then we can just draw towards the asymptotes. And all these points that are minimums at -1 will stay -1. And we have the graph of secant. Which leaves us the last graph, which is a little bit messed up. Sorry about it, may as well. We're going to graph cotangent. Now, technically, cotangent is 1 over tangent, and technically, cotangent is also cos theta over sine theta, and they're slightly different. Not a lot different, but slightly different. So we're going to talk about where they're slightly different. First of all, okay, for tangent, yeah, we'll talk about where they're different right away. We're going to talk about pi over 2. On the tangent graph, pi over 2 and on your unit circle, that's a non-permissible value. It says not possible right at the top of your unit circle for tangent. So tangent to pi over 2 does not make sense. So according to that, if you graph 1 over tangent, pi over 2 would not make sense. But if I plug in pi over 2 for this, cos of pi over 2 over sine of pi over 2, what do I get? Cos of pi over, well, this is good practice for your unit circle. Cos of pi over 2 is 0, sine of pi over 2 is 1, then you get 0. So mathematicians had to make a decision. In graphing cotangent, is graphing cotangent more like 1 over tangent, in which case pi over 2 is not allowed, or is it more like cos theta over sine theta, where it is allowed and equal to 0? And they decided it would be allowed and equal to 0. So this is like the exception for cotangent. Wherever you have these original x-intercepts for tangent, the graph of cotangent is more like cos theta over sine theta, and all of those will become x-intercepts. The rest of your graphing, like the reciprocal, stays the same. Wherever tangent is 0, we will have vertical asymptotes. Because you might notice, if you think of it as cos theta over sine theta, all of these asymptotes are exactly the places where sine of theta is equal to 0 as well. Oh, there's so many. So happy about this. I don't know if that therapy is working anymore. A little violent therapy. And this is where cotangent is also messed up. Your tangent graph goes up forever, which would normally mean an asymptote at y equals 0. But because we have all of those x-intercepts at y equals 0, there is no horizontal asymptote for cotangent. Again, because in cos theta over sine theta, there would be no horizontal asymptote. You know that tangent of pi over 4 is 1. Does it make sense that cotangent of pi over 4 is also 1? In fact, anywhere where the graph is 1, it'll stay the same. And anywhere where the graph is negative 1, it will also stay the same. And so with those points and those asymptotes, the graph of cotangent is sort of like a backwards graph of tangent. I think the cotangent graph has shown up on the exam 3 times in the past 24 years. It doesn't come up very often, right? But it's just when you think it won't show up that they'll probably, they should have, right? They should have betting odds. They have betting odds on everything. You should have betting odds on what you think is going to be on your provincial final, right? Like, it'd be like consolation. It's sort of like, I failed that exam. No idea how to graph cotangent, but I won $1,000. Because the odds for cotangent to be on the exam were at 150 to 1 or something. So these are your reciprocal graphs with trigonometry. They sine, I mean the cosecant and cosecant seem to show up more often than cotangent, but it's the same rules for graphing, except cotangent has a couple of specialty things. So you have to study that a little bit extra.